Welcome on board the Richplanet starship, broadcasting from somewhere high above the Earth. I'm Richard D. Hall, and we'll start things off with some news. Last Wednesday, the new Prime Minister, David Cameron, named his new cabinet. And before he had convened the first proper meeting of that new cabinet, which took place on Thursday, on the Wednesday evening he met with intelligence chiefs. This meeting was the first of the newly named National Security Council. At this meeting, intelligence chiefs briefed David Cameron about the situation in Afghanistan and the anti-terror situation in the UK. In other words, before David Cameron had a chance to try out the number 10 Bath, the paranoid intelligence agencies who actually orchestrated 7/7 and support murder in their illegal occupations of foreign countries insisted on briefing Cameron at the earliest opportunity. This isn't surprising, as more people every day are learning the real truth about 7/7, and the intelligence agencies are desperately trying to keep this information away from politicians and the public. I doubt very much if you could obtain minutes from that particular meeting. But that's okay, because it's a matter of national security, so it's safer that we are not told. I would speculate that they have been warned what to say and what not to say if challenged on 7/7. I would also imagine they have been told to be very economic with words on a range of issues, including terrorism, the drugs trade in Afghanistan, and perhaps even aerial phenomenon such as UFOs. But more on that later. Meanwhile, the career politician and Bilderberg member William Hague, who was making political speeches at party conferences when he was still in short pants, popped over to the United States to meet his Bilderberg counterpart, Hillary Clinton, where he stated that Britain would support dropping bombs on Iran if America wanted us to. Well, you don't speak for me, William, and you don't speak for 3/4 of the British people, you bald-headed little ponce. It's time to introduce this week's guest onto the starship, and I'm delighted to welcome back the man who can explain life, the universe, and everything in a way that nobody else can. He's the author of Relativity Plus. So let's activate the teleporter and get him beamed up onto the ship. It's John Duffield.
Hello, Richard.
Are you okay?
Yeah, lovely, thanks.
Good, good. Now, the last time you were here, we were talking about particles, and we were looking at these particular knots that you believe are essentially the electron and the proton are basically photons going around tied in a knot. Would you care to just summarise that for us, John?
They're not quite photons, but in simple terms, yes.
Okay.
They are, in essence, stress energy or light.
Mm-hmm.
The neutrinos are a little different, mm-hmm. But yeah, that's in essence what they are. They're stress energy configurations trapped in a dynamical pattern,
okay,
which we describe as knots.
And just to go back a pace, if we consider everything in our world, this table, all matter, it's made of molecules. You would describe it as molecules, and the molecules are constructed of atoms bonded together, and those atoms are then made of particles, which is... Could you list the fundamental particles that make up all matter for us, John?
Well, the really fundamental thing that makes up matter is energy. Mm-hmm. We talk of elementary particles, but they're elements of matter rather than being something that you cannot reduce to anything else. Mm-hmm. You can reduce a proton plus an antiproton into, in essence, light. Okay. So you believe that everything is essentially space and ripples in space. Would you go along that? Yes.
Or stresses in space.
Energy or stress energy is a ripple in space. Mm-hmm. However, space itself, even if there's no photons travelling through it, it has its own energy. It has a stress, a pressure.
Okay. And this is one of the fundamental things which sometimes people don't realise, is that if you have a vacuum, nothing there, no energy, well not no energy, but just what appears to be a nothingness, It's not nothing, is it? It's
No, space has its energy. People talk about virtual particles, but they're virtual. They're not real particles. In essence, it's a calculating facility. Virtual particles are rather similar to the virtual pennies that go into your bank account when you get paid. There are no actual pennies flying into your bank account.
Right. Yeah. Yeah. Okay. Well, so just to summarise then, all particles, all matter is essentially light going nowhere fast. Would you?
I'd say an electron is a photon going round and round and round. It's travelling at the speed of light, but it's not getting anywhere.
Okay. And that energy that it has then is what appears as mass.
The
fact that
energy momentum, the momentum aspect appears as inertia, but yeah, the energy looks like mass. That's why we have E equals mc squared. Einstein's paper back in 1905, in essence, worked that out.
Okay.
He said, a body that gives off radiation, in essence, light, loses mass.
We've talked about quantum mechanics. What's the point of quantum mechanics? Why was it needed?
To explain observations, there's something called the black body problem. This goes back to 1905 when Einstein wrote his paper on quantum mechanics. That's what he got his Nobel Prize for, not relativity. He was in on the ground floor of quantum mechanics.
Right.
He, in essence, worked out that photons must have a quantum nature.
Right.
Now, that doesn't mean that they are little billiard ball particles, but they just have a quantum nature.
And you would say that that quantum nature is in the amplitude of the photon. Is that?
Yeah, it's an amount of displacement or extension that is in the wave or the pulse as it ripples through space.
Okay. So a photon has a fixed amplitude, but we can't really postulate why that is, can we?
Not quite,
We don't
no.
really know why space, when it allows light to pass through it, will always vibrate at that displacement level.
Well, no. It goes back to Planck's constant of action. Action is, in essence, kick. If it's a high-frequency photon, it's a fast kick.
Yes.
If it's a low-frequency photon, it's a slow kick.
Yeah.
But the length is always the same.
Right. Okay. Okay. And quantum mechanics, because I mean I might be wrong here, I thought it was explaining things as point particles which have a certain randomness about their position. Is that correct or not?
Some would argue that it is correct. I think it isn't. If you look at something like the Heisenberg uncertainty principle, it applies perfectly to a wave. You can't say that the wave is in any one particular position. We know that photons can be 1,500 meters in wavelength because of long wave radio. There's no point particle in there. We know that photons are used to make electrons. There's no point particle in there either. Ditto for a proton. There are no points. The quarks are not points.
Okay, so it's not really a random quality, is it then?
It's
because if you're saying that it's a wave, you can predict at what point in the wave, you know, sorry, I'll rephrase that. You can predict whereabouts, you know, the contour of the wave is in space. So it's not something which is random then.
No, but if you are looking for an interaction, you're going to say that that interaction takes place at a position.
Yeah.
And that makes you think in terms of points.
Right. Okay. Okay. And Einstein said God does not play dice. Is it?
Einstein had a lot of arguments about the Copenhagen interpretation of quantum mechanics. He didn't dislike quantum mechanics. He just liked this interpretation that said things don't exist until you look at them.
Okay. Okay then. So just to recap, particles are essentially made of photons wrapped in a particular knot. Would that be true to say?
Not quite,
Not
but
quite.
for the electron, yes. For the proton, you have to consider neutrinos. Neutrinos aren't photons, but they have little mass, not much charge. They're actually quite similar to photons.
Right.
They're classed as leptons like the electron, but you could say they're, in essence, dark light rather than dark matter.
Now, well, let's move on to gravity then, because your model of the photon basically can describe where gravity comes from, or the stress in space, isn't it? If you just describe that for us, John.
It all comes back to electromagnetism. The photon is an electromagnetic wave. You have a variation in the electric field and the magnetic field. There's only really one field there, so there's a field variation. Now, the speed of a photon, c, depends upon the vacuum impedance of space.
Right, this is the speed of light.
Yeah.
Okay.
If permittivity and permeability are different, then the speed of light is different.
So this is how easy the wave finds it to pass through space, shall we say,
Yeah,
whether it has got resistance or not.
Vacuum impedance is talking about impedance. Impedance is resistance to alternating current rather than direct current, and the photon is, in essence, a form of alternating current. There's no electron moving back and forth. There is no charged particle there, but you do have a field variation.
Okay.
Therefore, there is a form of current, and it's akin to displacement current. So, if you've got current moving through space, if you then think in terms of twist and turn, that means the permittivity is telling you how easy it is to twist space, and permeability is actually the reciprocal of turnability.
Right.
It's how good the space is at turning you.
Right.
So you get back to this elastic idea, and as a result, you can see a gravitational field as a variation in the speed of light because the strength of space has changed.
Right.
Now, Einstein actually talked about the variable speed of light a great deal. He started off in 1911 with a particular paper. He talked about it again in 1912, 1913 and 1915. People think he was talking about velocity. Velocity is not quite the same as speed, but when you read the original German, the words he used translate into a variable speed of light.
Right.
What he said was that the light curves because its speed varies with location. So it's a little bit like a swimming pool. Imagine that every morning you swim up and down the pool. But one night I sneak in a load of gelatine powder and I tip it all the way down the pool. And the next morning when you swim down the pool, you notice something's not right. And when you look back at your wake, you find that your path isn't straight anymore. It curves, it veers. Gravity's a bit like that. The viscosity or elasticity or strength of space is higher near the planet than it is a long way from the planet. Therefore, the path of a photon veers. Your curved wake is, in essence, curved space-time.
So, away from the Earth, light finds it easier to pass through space because there's less stress in space. Am I right?
It goes through space a little bit faster.
Yeah. And then as you come towards the Earth or any matter, the space is more stressed, so therefore light goes slightly slower through it. Its progress is slower.
Its progress is slower, it moves slower, and it's a little bit like a
Hence,
car.
light going past the planet will be bent towards it like this.
Yeah.
And then what we will do is we will in the next section we will describe, or let you describe, how that can affect matter, not just light. Because that analogy that you've given there is how light, i.e. a photon, is bent, but it has the same effect with mass, doesn't it? And
yeah, it's simple to work out.
Okay, right. Well, we'll be speaking to John some more after this short break. Welcome back on board the Starship, and we're talking with John Duffield. And before the break, John, we were talking about how light is affected by gravity and how it is actually bent. You explained that. So how is matter actually attracted by gravity? How does that work?
It's quite simple. We talked about the simplest particle, the electron, being in essence light going around in circles. If you imagine that swimming pool where there's a viscosity gradient and you're swimming not straight up, but you're swimming round in circles. Now, make it a bit simpler by imagining you're swimming round in a square rather than circles. Whilst you're going up the pool, you veer a little. Whilst you're coming down the pool, you veer a little. So what actually happens is that you work your way over to the left. That's in essence how matter falls down. The gradient in space bleeds motion out of the circulation into a linear falling motion.
Okay. So let me try and repeat that back to you to make sure I understand. All matter is essentially light going round in a loop of some kind, and when we have gravity, we have a piece of space which has a gradient, as it were, in terms of the resistance of light. So when light's going that way, it veers, and when it goes down, it doesn't veer, and then when it comes that way, it'll veer again. Yeah. So when it's in a certain orientation, it will veer downwards, and that is what the gravitational force is then? In essence, yes. Right, okay. And again, would that be an accepted view of it, that gravity is a gradient of stressed space? Is that what you would call it?
People do tend to talk about curved space-time, but there is considerable debate within physics about what Einstein actually meant.
Right, okay.
And you can see in papers of his what he was actually saying, and it seems to be pretty clear. He talked about inhomogeneous space. He talked about empty spaces not being empty. He spoke of gravitational potential. You can easily see this in the terms we describe. A gradient in space causes curvature.
Okay, so if we consider the planet, okay, we've got a large mass at the centre, and as we go further out, this gradient reduces, okay, which means that the gravitational force further away from the planet is less as the further you get. Now, why, because you have mass here, why does that cause this stress gradient in space?
Well, matter itself doesn't cause it. Energy causes it.
Right.
You can think of this as, imagine a cube of pressurized jelly. Now, inject more jelly into the cube.
Yeah.
You create a pressure gradient around the center.
Right.
This alters the properties of space such that something going through the space doesn't go straight anymore, it veers. And if you've got something going round, it either falls to the planet or it falls to the planet, because it's always veering in the direction of this concentration of stress energy.
Right. And am I right in thinking that matter is attracted twice as much to the gravity as to what light is?
It's half.
Oh, sorry, half.
It's like this swimming pool analogy where you're swimming around in a square, only that portion of the square veers. This portion doesn't. This goes straight. Right. This portion veers. This portion doesn't. So 2 out of the 4 portions are subject to the veer. Therefore, matter is affected half as much as light.
Half as much as light, because it's going round in a circle, and only 50% of its motion, if you can use that word, is being pulled by
50% is orthogonal to the gradient.
Yes. Yeah. And this explanation of gravity, John, how well accepted is this?
I'd say it's not very well accepted, but it's been around for quite a while. I didn't invent it. There are physicists such as Albrecht Geis who've come up with it. It was talked about in 2004 quite a lot, but I've not seen much recent talk about it. I actually found this explanation in a paper talking about ether theory. A lot of people don't like the sound of ether, but Einstein actually talked about it in 1920 in his Leiden address, the title of which was Ether and the Theory of Relativity. And there he's talking about space as ether, which is quite a surprise because typically people think that relativity dispensed with the need for an ether. Einstein talking about ether was quite a shock to me.
Right. Okay, and if we just go back to the previous program, we said that electric charge is essentially a twist in two different orientations of space, and what you're saying, that gravity is a stress in space. So in other words, it's a change in shape or a distortion of space, but they're similar but not the same, aren't they? So electric charge or electromagnetism and gravity, but they're both distortions of space. Would you agree with that?
Not quite.
Right.
Electromagnetism is the result of curved space. At the heart of it, you've got a photon going round and round. Light travels in straight lines. If it doesn't, you have to say the space is curved.
Right.
Now, in gravity, it's actually a pressure gradient.
Right.
The curvature is what you see when you apply motion. If you, for example, think of this room as curved space.
This spaceship is curved.
If, for example, you think of this spaceship, this cat.
Sorry, John.
If you think of where we're sitting as
Yeah.
consisting of curved space, then if I threw a ball, regardless how fast I threw the ball, it would always travel in the same curved path. Curved space-time is where the curvature of the ball depends on how fast I throw it.
Okay. Right. I think I understand. But essentially, gravity and electromagnetism are basically space that has been distorted in some way. Would that?
Not quite.
Not quite.
You have to distinguish between space, that's distorted in electromagnetism, and space-time, that's motion through space,
Right.
that's distorted in gravity.
Right.
Again, gravity is a pressure gradient which alters the motion of light or particles.
Okay.
In electromagnetism, the particles consist of light, which is going round and round and round because that's in curved space.
Right. Okay. And if we just consider charge, what charge does to space, it twists it.
Charge is the lockdown that affects the surrounding space by giving it a twist.
Okay.
It's a twist in two orientations.
Right. And gravity is more as like you're pumping more
Stress, more
more
energy
stress
into a region of space,
into a region of space,
which puts a pressure gradient into the surrounding space,
right.
which therefore affects motion through the space.
Okay. And the more energy that you have in a smaller space creates a higher stress.
Stress energy is the word for it. When you pump energy into space,
Right.
in essence, it's rather like the space expanding and putting pressure onto the surrounding space.
And there are two similarities with gravity and charge in that they both follow the inverse square law. The further away in distance you get, the less the effect is by the square. So they're similar in that regard, but they are different. And let's come on to time then, John, because one thing that was explained very well, I thought, in your book is time, and just go into that for us.
When you actually look at what time is, the sort of thing you perhaps look at is a clock. Now, when you open the back of a mechanical clock, you don't actually see time flowing. You can't see any evidence that we travel through time. All you can actually see is little gears and things moving. Now, if you have a quartz clock, all that's happening is that the crystal is oscillating. If you have an atomic clock, it actually uses microwave radiation. And there's a detector which counts the microwave peaks that come into the detector. All forms of clocks rely upon motion. They clock up motion, not time. If you think about a day is based upon the motion of the Earth. A year is based upon the motion of the Earth around the Sun. All measures of time are in fact measures of motion. So when we talk about time travel, it's not founded on any scientific evidence. The motion is through space, it isn't through time.
Okay, and because all matter is essentially light, if that light moves faster, then our time seems to speed up.
Well, it's like pressing a fast forward button.
Yeah.
The motion speeds up, not the time.
So in other words, if you move to an area of space which is less stressed, let's say lower gravity than where we are now, time will move faster. And that's proven, isn't it, John?
Well, time doesn't move faster.
Sorry.
Motion through space occurs at a higher rate.
So in other words, the waves that make up the particles of us travel faster than they would in an area of stressed space. So therefore, the watch on our arm would move faster than somebody else's who was on the surface of Earth.
Yeah.
I'm talking about the fact that away from Earth, you've got less gravity, therefore space is less stressed. So therefore, light moves faster slightly. Therefore, our time appears to move faster.
Yeah. This is why we have the GPS clock adjustment. The clocks are set to run at the right rate for the altitude that they're going to be at.
Yeah.
There's two effects which actually go in opposite directions, but the net effect is that those clocks up there go faster than they do down here. And what's actually happening is that the motion inside the clocks is going faster.
Okay then, John, well, we're going to talk more after the break. It's time for this week's Artist of the Week. And this week we're featuring Neil Saunders' band, Thought Crime. Now, Neil produces ska punk songs which deal with subjects such as mind control and New World Order techniques. This track is called A Series of Techniques, and it features Aldous Huxley, who's the author of Brave New World.
That we are in process of developing a whole series of techniques which will enable the controlling oligarchy, who have always existed and presumably always will exist, to get people actually to love their servitude. People can be made to enjoy a state of affairs which, by any decent standard, they ought not. I think are a real refinement on the older methods of terror, because they combine methods of terror with methods of accept other methods which one can think of. There is, for example, the pharmacological method. This was one of the things I talked about here in Brave New World. The result would be that a euphoric which would make thoroughly happy even in the most abominable circumstances.
Injections and injunctions will combine from a very early age to produce the sort of character and the sort of beliefs that the authorities consider desirable, and any serious criticism of the powers that be will become psychologically impossible. Bertrand Russell.
Over 100 years ago, eugenicist social planners said that they'd use mind-altering drugs to control the population. By 2007, more than 20% of the U.S. population were on some type of prescription antidepressant.
Welcome back on board the Starship, and we are joined as usual by the Starship pet, Ulysses. Okay, now this week's interesting person of the week is David Cameron. Now before you reach for the remote control, some of you may be aware that in January 2009 I asked David Cameron, when he becomes Prime Minister, will he lift the veil of secrecy about UFOs? Now I've had quite a few emails and feedback asking me if I'm going to contact David Cameron again. And quite often I do get emails saying things like, which annoys me a little bit, things like, well, David Cameron would never have the authority to reveal information on UFOs. It wouldn't be up to him. He wouldn't be party to the information. It would be up to the Americans, etc., etc. Well, do you think that I don't already know this? Asking the question isn't necessarily to get an actual answer, because firstly, it brings more awareness to the subject, and secondly, it has opened a path of communication between me and the Prime Minister. But let's just take a look at the clip first.
Sir.
In July last year, the respected scientist and astronaut, Dr. Edgar Mitchell, who was the sixth man to walk on the moon, spoke on a British radio station. He said that the American government had had contact with extraterrestrials on multiple occasions and that these were ongoing. He spoke about the Roswell event of 1947, where wreckage from a downed UFO was recovered and found to contain alien bodies. He said that this event was real and had been covered up by governments for many years. Do you agree with me, David, that the British people have the right to know if we have been visited? And if so, when you become Prime Minister, as I know you will you seek to lift the veil of secrecy and tell the public the truth that they deserve, that has been covered up for all of these years?
Thank you. Thank you very much. Well, I told you I didn't plant the questions. I'm convinced we have been visited by alien life forms, and one of them is the Trade Secretary, Peter Mandelson. But quite seriously, sir, no, because I'm going to give you a serious answer. I'm going to give you a serious answer.
I don't want anyone to take the subject.
No, I'm going to give you a serious answer now, honestly. You can have the mic, after I've finished, you can have the microphone back. No, look, I think I have no idea whether there is intelligent life out there, and no idea whether any sightings that have taken place or incidents that have taken place have any basis in truth. All I know is I do believe in freedom of information and openness, and if this question has been asked from time to time of governments in this country and indeed in the US, and I think we should be as open and as clear as possible. What's tended to happen when people look at the Roswell incident or people look at pictures and other things that have happened, is a rational explanation tends to be produced to try and show that it's not what those who believe in UFOs suggest. But I think we should be as open as possible. So I'd be quite happy to give you a guarantee that if I was Prime Minister, I would always be entirely open and frank about these things. I don't think any of us have any clue whether there is any intelligent life out there, and it's certainly not something that any government should seek to hide from anybody.
Now, after that interchange took place, I actually wrote David Cameron a letter asking him if he would be interviewed on my TV show, not specifically about UFOs, but about world peace and various other issues. And he wrote back to me in person, and this is the letter, signed by David Cameron, in person, on yellow paper. So he wrote me a personal reply. Now, he declined to come on the programme. However, because he wrote me a personal reply, I decided to write to him. And I wrote him, well, a one-page letter, basically telling him the situation on UFOs and what was known by President Kennedy and various other very important points. Now, this letter was acknowledged, so I believe that David Cameron has actually read that letter. So, yes, David Cameron probably isn't the one who would make a decision to tell the truth about UFOs, but at least it's a start. He has had the information, and he remembers that meeting because there's an article here. This is from April the 10th, 2010, this year, and he actually states here, so it's a very long interview with David Cameron, and he says here, "I once had a question on aliens, you know, up in the northeast." So this is quite a recent article. So that question is obviously still on his mind. And this week's interesting scientific fact of the week is ostriches' eyes are bigger than their brains. And we're talking with John Duffield, who is the author of Relativity Plus, a theory or the theory of everything. Now, we were talking, John, about time and about how motion moves at different rates if you're in an area of low stressed space or high stressed space. But this is fundamental to Einstein's theory of relativity, isn't it? In that your local speed of light fundamentally controls the rate at which your motion progresses, i.e. how fast your time is. Could you explain that for us, John?
Well, we measure time on clocks. Clocks use motion. If the motion goes slower, we say we're time dilated. We say the time goes slower, even though we can't see time going anywhere. Mm-hmm. It's just a measure of motion, yes. A cumulative measure of motion. Mm-hmm. Mm-hmm.
So what happens then if we, let's say, move at a very fast speed, half the speed of light, let's say?
And simply the motion through the universe mm-hmm. comes at the cost of your local motion, mm-hmm. which occurs at a reduced rate. Mm-hmm. You can't tell because it affects everything, mm-hmm. electrons, protons, mm-hmm. clocks, rods, everything.
Yeah.
You can't tell the difference.
Mm-hmm. So if you just consider, we said before that the electron is essentially a photon in a knot. If you consider that photon, it's going around like this, but at the same time it's moving. But it can only travel at the speed of light. Therefore, its progress around that circle is slower. So your time appears to slow down.
Exactly.
That's how relativity. And really, does this not back up your theory that all particles are light? The fact that you get time dilation.
It isn't really my theory. But in essence, yes. So you can think of the electron as a photon uh-huh. going round, and if that electron's travelling, you can think of it describing a helical path.
Yeah.
And the speed of the photon is the speed of light.
Is whatever your local speed of light is, which depends on how stressed the space is where you happen to be.
Depends on the space, yeah.
Yeah. And if you move at a certain speed, your time appears to slow down because all of the molecules in your body start effectively running at a slower rate, I guess. Is that
all of the local motion mm-hmm. is happening slower because of the motion through space. Mm-hmm. Mm-hmm.
Yeah, and would you say that that's the essence of what relativity tries to describe? Then, the fact that
I think in 1908, mm-hmm. Minkowski described it in terms of space and time, mm-hmm. but later in life, Einstein started thinking more in terms of space and motion.
Right.
There's a very interesting book called A World Without Time. Mm-hmm. Which gives some of the discussions that Einstein had with Gödel in 1949. Mm-hmm. A very interesting book. This shouldn't suggest that time does not exist. Mm-hmm. It just isn't quite what we think it was. Mm-hmm. In that it's a little bit like temperature. Mm-hmm. You can't actually move through temperature.
Yeah, I've got the quote here from your book, John. Can I just read it?
Sure.
It's time exists like heat exists, being an emergent property of motion. It's a cumulative measure of motion used in the relative measure of motion compared to the motion of light, and the only motion is through space. So time has no length, time doesn't flow, and we don't travel through it.
Exactly.
Okay. Right, now we've touched on gravity, we've touched on time, we've touched on matter, we've touched on energy. Can we discuss dark matter? Because that seems to be quite a sort of a topical thing at the moment?
Yeah, it seems very simple. Of course, there is matter out there and it's dark. There are little planetoids. Neutrinos are legitimately classed as dark matter. However...
So just 1 second, John. What's the difference between a photon and a neutrino then? Is a neutrino is a particle, is it?
It's just a different type of wave.
Right, okay.
We talk of wave-particle duality. It's best to think of all particles as waves, some of which are waves that are tied in knots.
Right, okay.
The neutrino is better thought of as a running loop,
right,
or a rolling wave, rather than a transverse wave.
Okay, okay.
So
dark matter.
As regards dark matter, once you understand that space has energy, you know from E equals mc squared that energy has a mass equivalence. So even though you can't see this space, if it has energy, then a block of space does have a mass equivalence. Now, if space is not homogeneous, if it's not the same everywhere, then if you had a region of space where the energy density was higher, then that would actually behave as if there was mass there.
Right.
So you'd start looking for dark matter, but you can't find any dark matter particles because it's the space that has more energy, and therefore it's the space that has this mass equivalence.
Right. Okay.
Now, I don't know if you've ever heard of the raisins in the cake analogy for the expanding universe.
Right.
This is where the universe is portrayed as a cake that's rising. The galaxies are the raisins in the cake. Where the galaxies are, space is not expanding. Now, what this means is that the space cannot be homogeneous, in that if it was dense in the galaxy and it was dense around the galaxies, then after space is expanded, it's dense here, but it's less dense here.
Right.
So you've got a gradient in space between the galaxy and the surrounding space.
Right. Right.
The space is not all the same density, therefore you have this mass equivalence effect kicking in,
Right.
which causes gravitational anomalies such as lensing
Right.
or flat galactic rotation curves.
Right.
You go looking for the matter that caused it, you can't see it.
So this dark matter is not in the form of particles then? Is that?
We can't find dark matter particles. There's a number of searches ongoing. They haven't been very successful. And I think it's pretty obvious, if space is the way Einstein described, that the energy of space in a gravitational field causes gravity. In a gravitational field, you don't go looking for dark matter particles. You know it, the energy is in the space.
And you believe that there is energy prevails throughout space, which I think Tesla originally said. Do you go along with the zero-point energy theories that space fundamentally has energy locked within it, that we if we could only tap it, would be the solution to the energy crisis?
I'm not sure we can tap into it, but certainly space has its vacuum energy.
Right.
You look up at the night sky and space is dark, and there's energy to it, and you shouldn't really be wondering about dark energy. Space has got this stress. Something stressed, like a stress ball, if you let it go, it expands.
Now, we were talking about gravity before, and obviously you're aware that I'm very much into UFOs, and often that people describe anti-gravity. Now, what's your beliefs on anti-gravity? Can it exist? Or I don't like the word anti-gravity. I like the word other gravity. They generate gravity somehow.
I think that's a good way of putting it. In theory, one ought to be able to make an artificial gravitational field, whether you use magnets, superconductors, or something called the evanescent wave. In theory, I think it should be possible. If you can create a gravitational field above your head to counteract the Earth's gravitational field, then you wouldn't fall down.
Yeah.
If you increase the strength of this gravitational field, you would, in theory, go up.
Yeah.
However, conservation of energy applies. You cannot go up because it takes extra energy.
Right.
You have to put that energy in somehow.
Right.
Escape velocity is about 11 kilometers per second. So
Right.
if a body falls from altitude to the surface of the Earth, that's how fast it's going. A lot of energy.
Okay.
If you want to get away from the surface of the Earth, you've got to put that energy into the system.
Okay, so if we assume that UFOs exist, then they must have advanced energy systems or power systems, you would imagine.
As Hawking said, one would be foolish to presume that there's no other intelligent life in the universe. I think it's reasonable to expect that when pilots tell you about craft doing a sudden stop and then swooping back over the top of the plane, there's some way there to remove the effects of gravity and inertia and creating an artificial gravitational field. Sounds like the way it ought to be done.
Yeah, because the dynamics that are seen on radar, you know, if they were explained in conventional ways, the G-forces in there would be phenomenal, wouldn't they?
But they would.
But if you explain them in terms of generating your own gravity field, then there are no G-forces.
You're always in free fall. You don't bash your head against the windscreen.
Yeah, okay. All right, and John, well, just where can people get a hold of this book,
from
Relativity Plus?
From Amazon.
From Amazon?
Yeah.
Okay. Right, and it is a superb book. It cleared up a lot of things in my mind, John, and the illustrations are excellent, very, very well illustrated, and with very few equations as well. I mean, there are some equations in here, but you know, if you're not of a physics background, you can still read this book and get a lot out of it, can't you, John?
Yeah, I hope so.
Okay.
And even if you do, then there's references in the back to the source material. There's a lot of people who've written some very good papers, which tend not to get noticed. They can then follow up on those papers to get the equations and the detail and find out who wrote the papers. Most of what I've said here is derived from those papers. That's why the book is dedicated to the unsung heroes of science.
Yeah, yeah. There's a great quote in here where you talk about the Hadron Collider, and they're saying, well, the Hadron Collider, we're building it because we don't actually understand everything and we're wanting to learn more about the universe. So how can they be so sure that it's safe if they don't know everything? That was...
I think there's been some unfortunate publicity to do with the Large Hadron Collider. I do wish that they'd talk more about the energy benefits that might come out of it.
Right.
The talk about black holes and safety, I think that was ill-advised.
Right.
I really do.
Okay. What do you mean What do you mean by that? That you think it's not safe, or?
I think it's safe. If I thought it wasn't safe, I wouldn't be sitting here happily. I'd be campaigning. I'd be doing everything I could.
Right.
But the all of the furore about it not being safe was in part generated to gather publicity.
All right. Okay. By CERN themselves.
When you go onto the CERN website and search on black holes, you can see papers by scientists, not necessarily CERN scientists, who are using this for the wow factor in order to attract attention to themselves.
Right.
Science is very competitive.
Okay then, John. Is there anything else you want to say?
Thank you very much. It's been very nice to talk to you, and I hope that I can do my bit for physics and help out with the issues that physics can solve.
Okay then, John. Well, thanks very much indeed for coming in, and we'll get you beamed back down to planet Earth.
Thank you.
Okay, it just remains for me to say, keep your eyes on the skies, your feet on the ground, and tell all your friends about this show.